And welcome back to 13.4. We're going to look at our last phase diagram. It's the phase diagram for carbon dioxide. And the first thing we want to point out is the scaling of this diagram. Notice that you have 1 atmosphere of pressure, which is right here. That's the norm. That's what the average pressure is at sea level. We're above sea level, so we have a little bit less pressure. But we'll just say that we're at approximately 1 atmosphere of pressure. All right, here's where carbon dioxide is pretty interesting. If we are at cold temperatures at normal pressures, we're going to say we're going to be right here at letter A, you're going to be at the solid phase. But as you warm up carbon dioxide, notice that the very first boundary that you come across is the boundary between solid and gas. And so right at this point, we'll call that point B, you're going to be undergoing sublimation. And then as you continue to warm it up, it's going to be carbon dioxide gas. Let's just say right there. So carbon dioxide goes directly from a solid to a gas under normal pressures. That's why frozen carbon dioxide is called dry ice, because it does not pass through the liquid phase at normal pressures. Now, does that mean that carbon dioxide does not exist as a liquid? No, it does not. According to the phase diagram, anything above, here's our triple point. The triple point is at 5.11 atmospheres of pressure and at about 56 degrees Celsius below zero. You have this corridor right in here where the carbon dioxide can in fact exist as a liquid. So if we heat the carbon dioxide gas up to, let's just say that this is 0 degrees Celsius right here. Then you apply a pressure to it. You can squeeze the gas into a liquid, and you can actually condense it into that liquid. Or if you have carbon dioxide frozen as dry ice, you can apply a very, very strong pressure to it. Okay, put it on as a solid under higher pressures, then heat it up. Then, in fact, you can melt the dry ice into a liquid. So yes, you can have liquid carbon dioxide, but it has to be at higher pressures. Now notice if you have carbon dioxide at 31 degrees Celsius. Now 31 degrees Celsius is a fairly warm temperature for us. Room temperature is around 20 to 25 degrees Celsius. So this would be a pretty warm summer day. At a pretty warm summer day, you have already reached the critical temperature. Remember, above that temperature, you're not going to have the liquid phase. You have what's called a supercritical fluid, which is not necessarily a normal liquid. All right, we're not going to get into supercritical fluids right now. All right, so what you should be able to do for your test here is to be able to identify where your solids, liquids, and gases are on the phase diagram. You should understand the triple point, the critical temperature. And if we plot a particular scenario, let's just say, again, we've already used A, B, and C. Let me just change my color here. Let's go with, say, a red color. On the test, I might give you point A, point B, point C, point D, E, F, and G. You should be able to tell me what you would need to do in order to go from point A to point B or whatever. If I say they're at point A and I heat the temperature up to point B, what's going to happen? Well, as you cross this boundary line, it's going to melt. If I'm at point B and I decrease the pressure down to point E, what's going to happen? Well, the liquid will actually start to boil at point E because it's along this particular part of the phase diagram, that boundary. If you're at point B and you heat it up to point C, you're going to actually undergo boiling as well. So you can boil it by heating it up or lowering the pressure. If I'm at point C and I drop the pressure all the way down to point D, nothing happens in terms of the phase diagram. If I'm at point D and I cool this thing down to point E, you can freeze it. If I take it from point D, I should have had this down to, say, that was G over there. Let's say call this H. If we go from point H and I lower the temperature to point G, you should understand that that it's going to cool the gas down, but then it's going to undergo deposition at point G. It's not going to condense into a liquid. So you should be able to plot your way around these phase diagrams, explaining what processes are happening, what you're doing to the pressure and to the temperature, and what particular phase you're at any given point. All right? That concludes 13.4 and also concludes Chapter 13.